Welcome back to ECE 442-542. I'm guessing you already can envision what you're going to be doing next week at this time. You won't be maybe on campus. It will be during spring break, but don't let that distract you from today's material. Homework number 3 is due tonight or today. Homework 4 is not due next Monday. It will be due the following Monday, and that's the 12th of March. And that will be concerned with discrete equivalents. For homework number 3, there's actually some additional material in Unit 3 if you would like to examine that. We have complex poles, a little write-up on that. You can do it either using complex numbers or you can do it using real numbers. And I'm going down the left side and the right side. It depends on how you want to pursue that. That's how it's sort of laid out pictorially in that discussion. Chapter 4, some of Chapter 4, that's not the full Chapter 4 of this discrete time system foundations or fundamentals, is on inverse E transforms, and they have some more examples on complex and real inverse E transforms. And then there's also a write-up on the region of convergence in unit number 3. There's a similar write-up in Unit 4 discussing discrete equivalents, and don't feel like we haven't ever talked about discrete equivalents. We've actually done that since the very beginning of the class when we said, oh, let's try to find a linear difference equation relative to a low-pass filter. Can we actually make a low-pass filter in discrete time from a low-pass filter in continuous time? And that's one way of finding a discrete equivalent. Finally, when you do return from spring break, that next Wednesday will be our second exam, just as a reminder. Today, what I want to do then is start in Unit 4, which is dealing with discrete equivalents. We'll look at what it means to, there's two different ways of sort of finding discrete equivalents. So there's two different scenarios or two different cases. And we'll actually look at the second case first, which is a zero-order hold equivalent, and we'll look at some examples of zero-order hold equivalents. Hopefully that concept will be clear after today's discussion. After that, we'll go into the other strategy or scheme, which is numerical integration-based discrete equivalents and pole zero matching discrete equivalents. So there's a lot of different ways for performing discrete equivalents, and they each have their own reason for maybe using those particular discrete equivalents. Really, when we say discrete equivalents, it's just a way to convert from an analog system or a continuous time system into a discrete time system. And there's many different ways of having a continuous time system. You could have a filter, think a low-pass filter. You could have a controller, maybe that's a proportional integral or a proportional integral derivative controller. That's maybe capital C of S. Or we might have a plant. We might have a system, an airplane, a car, some electromechanical system that we're trying to control. That might be our plant. And it may be an analog system or a system in discrete time. We, for whatever reason, might want to convert each of those types of analog systems into a discrete time version. So we might have a filter that's a discrete time filter, capital H of Z. We might have a controller that we now want to realize, implement in some computer hardware or some computing machinery. That we would then have as a capital C of Z, or for design purposes, we might want to now have a discrete time plant for this airplane or for this electromechanical system. We could have any of those scenarios, and what we want to do is get comfortable with that concept. Or another way of thinking of it would be, how do we understand what's going on behind this very simple function in MATLAB, where simple in the descriptor, C to D. But that's now capable of performing a lot of these discrete equivalents for us. And that's continuous to discrete. And if you want to learn more about it, you can invoke the MATLAB default and say help C to D, and it will give you information on the different arguments and the kinds of discrete equivalents you can obtain within MATLAB. However you want to think about this unit, you have a lot of different ways of doing it. One is just to say, oh, I want to know a little bit more about MATLAB. Well, now you have that as a motivator. Let's remind ourselves where we might be living or what we might be dealing with, and that's controlling a system or controlling a plant. Again, whatever you like to think of as a plant, that's what you can maybe envision when somebody says, oh, I'm controlling a system. That might be something, an inverted pendulum. How many people took an inverted pendulum to class today? Just one? It's a beautiful day. Did you ride a bike? That's my inverted pendulum. Essentially, a bicycle could be thought of as an inverted pendulum. Hopefully you keep it upright vertical, but if you don't, if it goes unstable, you're on the ground, right? But a bicycle, especially a unicycle, you could think of as an inverted pendulum. But that's now our system that we might want to control, and you as a rider have all of these signals floating around. You know where you want to go. You have some reference input you may want to get from home A to school B. You now know how to introduce this reference input into your system, and you as a gyroscopically controlled navigator, you have this very capable controller, capital C of S. And there might be some feedback dynamics, there might be some noise, there might be some bumps in the road, there might be a disturbance, some potholes that you have to negotiate. All of those are a part of a controlled system. What we want to do now is look at discrete equivalents, and I'm trying to suggest that there's two different ways, two different scenarios, two different reasons for wanting to go from a continuous time representation into a discrete time representation. One is if you have a filter. Let's say that you have a low-pass filter from 320A. Maybe it's your favorite fourth order Butterworth filter. And you now say, oh, I actually want to implement that with a computer. Well, now you'll need to figure out, how do I make this discrete equivalent? That's the first scenario. Or somebody might say, I have this analog controller. I don't want to have all of these analog parts, these resistors, these op amps, capacitors. I want you to now make that happen, that same functionality. I want that to occur inside this microcontroller. How do we now convert from a capital C of S to a C of Z? The other scenario or reason is if we now have a plant. Now maybe you have a bicycle and you don't want to play with differential equations. You actually want to describe it as linear difference equations. Now you want to convert this analog transfer function, capital G of S, into a G of Z. These two scenarios have two different ways of going about that computation. And in fact, the second one will focus on one way of finding a discrete equivalent, and the first one will have a handful of different ways. We'll do numerical integration approaches. We'll have three of those. We'll have a pole zero matching. Maybe we'll only have four different ways of doing number one. But that gives us now five different ways of finding discrete equivalents. And we have to figure out how to do that prior to exam number two. All of those different ways. So hopefully, if you did come in on an inverted pendulum, you have your helmet, because we're going to be going quickly through this material. You may need that hard hat, that helmet, to keep us safe while we're working through this. Here is a block diagram of reason number one. And really, this is what we're wanting to come up with, is that capital C of Z in this block diagram. We're not worrying so much about the analog to digital converter on the front end. We're not worrying about the digital to analog converter on the back end of that controller. We simply want to learn how to convert a capital C of S into a capital C of Z so that we can now forget soldering and desoldering all of these electrical pieces. I want to just plug in my microcontroller into that location that is interfaced with this system or plant G of S. Or another scenario is you now have a filter and you want to simply find its discrete equivalent, H of Z. Now maybe you want to have a high-pass filter, third order. How do I realize that in a computer or maybe in a spreadsheet with linear difference equations? That's scenario number one, or reason number one. Reason number two, which is what we will cover first, and which is only having one way of finding this discrete equivalent, is what we will call a zero order hold equivalent. And that's what we're going to focus on today. But it may not be that clear, the difference, but now what we want to do is all of these in this particular discrete equivalent, we actually want to incorporate the dynamics associated with the D to A and the A to D and put all of those into our eventual discrete equivalent, capital G of Z, when we go from continuous time to discrete time. Compare that highlighted collection of blocks with this highlighted single block. In scenario one, we're simply going from C of S to C of Z. In scenario two, we actually want to incorporate, if any of these input sides and output sides have some dynamic characteristics associated with them, we want to incorporate those into the net capital G of Z, the discrete time transfer function. So what we want to do now is examine how do we create this capital G of Z. If somebody gives me a G of S that I know is going to actually be controlled in a discrete way, meaning I'm going to pre-process this sequence of numbers that are being fed into this analog system by a zero order hold, and we'll define what we mean by that zero order hold. Then we will also, on the output side of that analog plant, we're actually going to take snapshots or look at the output at a particular sample rate or every capital T units of time. And obviously if we have a sampler, well, in this class, our sample rate is going to be the same on the back side as it is on the front side. We're not going to have multiple rates of sampling going on in this class. So let's now look at how we can put all of these pieces together. Now we have three different pieces. We have the original plant, G of S, and that is an electric circuit. You should be able to analyze that. Or it's a bicycle, or it's an airplane, or it's an automobile, or it's an electromechanical system. It's a robot. You now want to be able to have that capital G of S, and this you may not have to derive. Now I may just hand you a G of S and say, here's your plant, and you go, okay, now what? Well, now the trick is to find capital G of Z. Find its discrete equivalent. To do that, we want to examine the other pieces that are connected with this analog system. We have a zero order hold going into that analog system, and we have a sampler on the output side. Let's now look at those two pieces and see how do we incorporate their characteristics into the net aggregated transfer function capital G of Z. That's what we want to have and work through some examples before we get back on our inverted pendulum and go home. Go from B to A, right? Or B to C. I don't know where you're going after class. I shouldn't be making these assumptions, but I'm assuming maybe that you're going back to A to finish up your homework. And if you've already completed your homework, then you can go to C and D and wherever you want, okay? Explore the alphabet. Be my guest. Let's look at the output side, the analog to digital. Let's say that the output is some analog waveform, little y of t. We now want to convert that into a discrete sequence of numbers. We want to now process that through an analog to digital conversion step. What happens characteristic-wise, dynamically, when we take this blue analog continuous time waveform and we sample it? Just think of taking a picture, every capital T, and with each picture you're recording the numerical value that that output y of t has at a given sample period, capital T. At t, at 2t, at 3t. What we're doing now is simply replacing this continuous time curve with values of the output y, specific values. We don't know what's happening between 0 and capital T. We just know we have something at 0, we have something at t, we have something at 2t. We're not assuming that we know what's happening between those sample periods. Once we've sampled, once we've taken the picture, we just have this sequence of numbers. What happens between the continuous time and the discrete time or the sampled time in terms of dynamics? Are there any dynamics? And what do I mean by dynamics? In a dynamics class or in a controls class, what do I mean by a system has dynamics? What's another way of thinking about a system that might possess dynamics? Pardon? Time is important. If I said, here's an electric circuit and it possesses dynamics, what does that mean? Would it have only resistors? Would it have resistors and capacitors? Would it have resistor, capacitor, and inductor? What makes that circuit dynamic? Does it have a dynamic personality, that circuit? Poles. What gives us poles? What gives us poles in an electric circuit? That could be our system. Pardon?
Power storage, like
Some kind of storage, right? Some kind of memory. What has storage or memory? Oh, a capacitor. That stores energy in this electric field. So we're charging up this capacitor, then it releases, it charges, it releases. That gives us dynamics. That gives us memory. We have memory in our system. If we didn't have any dynamics, we could have a pure resistive circuit. And then whatever the input is, the output would be some scaled version of that input instantaneously. There wouldn't be any sort of gradual change or memory or storage involved between the input and the output. In this case, from the left side, the analog, to the right side, the discrete, is there any memory going on? Is there any kind of dynamic behavior happening? When we take this picture, what's happening? Is there any dynamics going on? And dynamic doesn't mean that it can't be fluctuating up and down. How hard is this? This is just a coin flip, isn't it? It's 50-50. Flip a coin. I don't know. What is it? Is it dynamics or not? At least I can have a 50-50 chance if I flip a coin. What would your guess be?
yes.
Okay. Sometimes our guesses aren't quite right. Okay. So there are no dynamics here. We have nothing going on between 0 and y of 0. It's there. Is there any difference between, is there, for example, the value at time capital T on the right-hand side, does that have any sort of connection other than, yes, it's connected, but in the continuous time, but are we using y of 0 to get to y of t? No, there's no real algebraic relationship or memory associated with those two. So in this case, all of that to say we don't have to worry about this output side. There are no dynamics. We don't have to worry about this A to D conversion process, so let's just move on. That was an easy problem to worry about. Now, let's look at the input side, which is our zero order hold or our digital to analog conversion process. This is now on the left-hand side. We're taking a digital sequence of numbers and we're converting that sequence of numbers into an analog or a continuous time waveform. And the zero order hold, that's supposed to be descriptive. That means that we don't do a first order or a second order or a third order hold behavior. A first order might be to draw a slope between where I am and where I'm going. First order just means just assume that you're constant. So a zero order hold would say, oh, when I go from digital to analog, now what I want to do is when I start at time 0, I'm just going to go and hold that value until I get the next update, which is at time step capital, or at capital T. There I'm going to now jump up to this next value and hold that constant until I get to the next value, which really says that I could think of this piecewise constant. I want to convert this sequence of numbers. If I plugged in these sequence of numbers to a motor, and let's say our capital T was quite large, what would happen? I would maybe hit that motor with 1. And then what would I do? Well, then I'd wait capital T and I would hit it with 1.5. What's the DC motor going to do? It's not going to know what to do because you're just going to hit it every once in a while with an amount, a voltage. But if we now said, oh, hit it with 1 for the duration, then it's going to start picking up speed. Then when we hit capital T, we hit it with 1.5. It knows how to respond to these analog waveforms. So this case does have dynamics, and we do have to figure out how to incorporate this characteristic into our capital G of Z formulation. So let's now look at the time response behavior of this zero order hold. What's happening when we go from this discrete sequence of numbers to a continuous waveform? And the way that we're going to do this is let's do it in a stepwise process. First, let's just say, let's apply a unit pulse which has a value of 1 to this operation I'm calling a zero order hold. And the way that it works is the way that I've drawn it between the left side and the analog version of that. If we now apply a unit pulse to this system that is a zero order hold, it takes the input and holds it for one time step. You give it another input, it holds that value fixed for one time step. You give it another input, it holds it fixed for one time step. Let's figure out how to describe that as a dynamic characteristic. Here's our input. We apply a unit pulse to this zero order hold, and now what's the output look like? If you had to sketch the output, let's say here's time, and now I'm saying this is now the pulse response of a zero order hold. The very first thing I'm doing is I'm starting with a value of 1. And what happens if this is now a zero order hold? What did I just say happens with a zero order hold operator, or a system that has zero order hold characteristics? What happens now after time 0? Anything? Pardon? It holds that value for how long? Until the next time period or the next sample period. So until capital T, we just hold this value fixed. Here, if I wanted to, this could be our input. Well, I'm getting ahead of myself. So I'll go back. There is our pulse response for this zero order hold. We hit it with a 1, and what happens? It holds that 1 for one sample period, capital T. How could you now find an equation that might model that in terms of basic waveforms? Here is the unit pulse response of a zero order hold. And if you wanted to now create this rectangular waveform out of fundamental building blocks, out of fundamental waveforms, what would be a way to get started? And I'll tell you, I've already given you a big clue when I started dashing in a red line before. What would that look like if we didn't stop it at capital T? If we just left it, it would be a unit step, would it not? So we could think of this as a u of t. So now we might have u of t, the unit step, but is that red dashed line equal to the blue? Yes or no? Another coin flip. No. It is for a while. It is for capital T units of time. How would we make u of t with something else be actually equal to that blue rectangular waveform? How could we make g sub ZOH, how could we build it up out of fundamental waveforms? Yeah, we just should subtract a shifted time step, unit step, can't we? So now if we simply say, oh, well, I can create that blue rectangle by simply saying, let me remove this unit step. That's been delayed by the sample period capital T. So now u of t minus u of t minus capital T is in fact the unit pulse response of a zero order hold, where that separation between u of t and u of t minus capital T is the sample period. Now put your ECE 320A hat on and take this into the frequency domain. Take the Laplace transform of this equation. And I'll do the most, so now let's frequency domain that time domain expression. Which really just means let's do the Laplace transform, and I'll do the hard part. I already hit the shift key. So I've done the left side of that equality sign. Capital G sub ZOH of S. What's the Laplace transform of the right-hand side? What's the Laplace transform of a unit step? If I wanted a Laplace transform little u of t, what is that? I'm going to give you the look. What's the Laplace? So you could plug this into the definition of the Laplace transform and derive that, but what's the, if I said Laplace transform a constant, what would you do? If the constant was c, what would you give me for the Laplace transform of capital C? It would be capital C over S, right? It would be 1 over S scaled by the constant C. In this case, our scaling is 1, so in fact, the Laplace transform of a unit step is 1 over S. Now, what's the Laplace transform of a delayed unit step? And if you want extra credit, if you're looking for it, not extra credit, if you're wanting partial credit, no extra. If you want a little partial, what could you do? Well, it's a unit step. It must have something to do with 1 over S, right? So you could say, well, it's minus 1 over S, I don't know, something. But that's giving me 0, so it can't be quite there. But now what happens? What happens when you delay? What does that introduce? Now we have our exponential. Now this is this e to the minus, and it's delayed by one sample period, capital T. It's e to the minus t naught s, where the delay was t naught. But in this case, our t naught is capital T. There is now the frequency domain representation of our dynamics of a zero order hold. It's 1 over s minus 1 over s times e to the minus ts. Or let's put that together. We now could say, well, that's capital G sub ZOH. Let me factor out the two terms and keep track of 1 over s. Or I could write that as 1 minus e to the minus ts all over s. And now I actually have a way of thinking about this block diagram in terms of frequency domain behavior. I have a way of modeling the zero order hold as capital G sub ZOH of s. G of s is just the transfer function of my system. And here is my analog to digital converter, which really doesn't do anything other than take pictures of the analog waveform. It doesn't introduce any dynamics. And what I want, so here's my zero order hold. And I want to now put these two pieces together. If I put these two pieces together and call that capital Y sub 1 of s, then I have 1 minus e to the minus ts over s times g of s. And this, what does that represent? Well, that represents the Laplace transform of the unit pulse response of the system. So if you put in a unit pulse, and you can sort of envision what that is, that's now just a pulse, and you apply that to your system, and in the frequency domain, it would look like capital Y sub 1 of s. What we want to do now is use that to actually find a discrete time representation of what that means. We know capital Y sub 1 of s is 1 minus e to the minus ts g of s over s. I'm just shuffling things around a little bit. I'm putting the s that was underneath 1 minus e to the minus ts underneath g of s. What's that doing? Well, that's just putting another pole in the denominator of g of s. And where is that pole located? Right at the origin. That's all I'm doing, and now I have to figure out, oh, how do I work with this non-rational expression, 1 minus e to the minus ts. Usually in 320, if you had some non-rational function of s, you got really nervous. Maybe. Maybe you just were oblivious and you didn't care. That could be a solution as well. That's okay. But in this class, you don't have to worry so much because that rational or non-rational expression, e to the minus ts, is in a nice way. Because that represents what? A delay of one sample period. And how do we know how to represent a delay of one sample period in the z domain? Z to the minus 1. How easy could this be? So now we're starting to get somewhere. Let's put all the pieces together. So now what do we have? Well, we have capital Y sub 1 of z. We could write that into two pieces. We could say we have a g of s over s minus an e to the minus ts g of s over s. And don't get too worked up about that g of s over s. That's just putting one more pole at the origin. That's all that g of s over s is representing. But now I'm going to try to talk our way through some handshaking that I'm going to say is going to be what we allow. This is the Laplace transform or the frequency domain version of the unit pulse response of our system. Let's now see what that looks like. Well, we want to now convert that into a capital G of z. Well, how do we do that? Well, first we're going to have to take that back into the time domain, so we need to inverse Laplace transform that. We'll sample that, and then what will we do with that sampled waveform? We'll z transform it. That's what I'm trying to now show in this next line, so don't get too hung up on all the detailed notation. What did I say? I want to inverse Laplace transform that, then sample it, and then z transform that sampled signal. First thing, I want to take that frequency domain back into the time domain. So I'm going to inverse Laplace transform capital Y sub 1 of s. And this will be a continuous time signal or waveform. Then what do I want to do? Well, now I want to sample it. So here's sort of my way of saying I'm going to sample. I've put in some dashed lines, but that just means I'm sampling this continuous time signal. If I've sampled a continuous time signal, then what's coming out of that dash is a discrete time signal. So this dashed line means that and this is what's hanging off on the output side. This is the sample with the A to D. That's what is happening over here on the right-hand side. That's this vertical bar. That's sampling capital Y sub 1 of s after it's been inverse Laplace transform. Now that I have a discrete time signal, a sequence of numbers, I can z transform it. So that now I can say, oh, z transform that. So this is what I'm wanting to do, and I would get frustrated having to write that down all the time. So this is the handshake, or this is the notation that we're going to use. I'm going to just say that instead of going through all of that, I'm just going to say that capital G of z, here's our handshake and a wink to absorb all of that we just did and say, oh, I'm just going to say that that's the same as saying G, or the z transform of capital Y sub 1 of s. I'm not going to include all of that other dashed vertical bars, etc. I'm just going to agree that when I write this definition, that's what I'm actually doing. I'm inverse Laplace transforming capital Y sub 1 of s. I'm sampling that, and then I'm z transforming the result. Well, if that's the case, if you'll bear with me on the handshake and a wink, now I can rewrite that capital Y sub 1 of s as what it was. Capital Y sub 1 of S is this two-termed expression. G of S over S and G of S over S delayed subtracted from it. So that now I have G of Z is now the Z transform of G of S over S minus the Z transform of e to the minus TS G of S over S. And now we remember what we are holding in our hip pocket. We know what e to the minus TS looks like in the Z domain. That's just a one sample period delay. That's a Z to the minus 1. So we can actually pull that outside the Z transform and replace it with this operator Z to the minus 1. We're going to note that e to the minus TS is the Laplace transform of a delay of t seconds. And we also know that the Z transform, which is what that script Z is doing on the right-hand side in that expression, the Z transform of a one sample period delay or of a t second delay is Z to the minus 1. That means that we can now write G of Z as the Z transform of G of S over S minus Z to the minus 1 Z transform of G of S over S. And now we just have to do one Z transform, the Z transform of G of S over S. So if you can find the Z transform of G of S from your table, and I'm giving you a different Z transform table for exam number 2 if you want to use it, it has Laplace transform columns and it has a Z transform column. And that would be ideal for this kind of a operation. You may need to know what is G of S, and let me put another S in the denominator. And now I just want to know what's that correspond to in that row of Laplace and Z transforms. This now says that I can say, oh, I have 1 minus Z to the minus 1 times the Z transform of G of S over S. So we've now derived the zero order hold equivalent of a plant, a capital G of S. Or you might hear this referred to as the pulse response transfer function. This arose from hitting a system with a pulse and finding its transfer function. And that's simply going to be then G of Z is equal to 1 minus Z to the minus 1 Z transform of G of S over S. If you're looking for partial credit and I say find the zero order hold equivalent of this G of Z, the worst you can do is write that down, and that'll give you 1 point out of 50 for partial credit. I said I was going to keep you around for a semester or two, right? You can't graduate in May. Look, who's that optimistic? No, I'm just teasing. Okay, so now we have capital G of Z. Let's look at finding these zero order hold equivalents for some particular situations. Hopefully we'll have time to get through a few of these. So let's say here is example number 1, and let's say that this is a system that's about as simple as you can get. It's a gain. What kind of dynamics does this have? None, does it? It's just gaining. So you put in an input, it just scales and produces an output. No memory, nothing going on. That's what we're assuming. So now let's suppose for this system, let's say that our system, G of S, is simply 5. It's a pure gain. And we want to know, what does capital G of Z look like, its zero order hold equivalent? Now you're really looking for points, so you draw this block diagram. You say, oh, a zero order hold equivalent, it has to be something is taking this sequence of numbers and holding them flat, constants, that's the zero order, and it's the hold. And then we're applying that to this gain of 5, and we're sampling the result. And we want to know, what does all of this combination do for us in terms of G of Z? What's the zero order hold? And maybe I should call that G sub 1 of Z, since this is example number 1. Maybe I should say this gain then is capital G sub 1 of S. We want the zero order hold equivalent of a gain. Or what is the pulse response transfer function of this gain? You now have this written down on your cheat sheet. 1 minus z to the minus 1, z transform of G of S over S. So you write it down. And you already know, in this case, we said, oh, let's just say that this is our first example. You know a little bit more about G sub 1 of S. Five over S. So in terms of a system, this now looks like an integrator, doesn't it? An integrator looks like 1 over S as an operation. 1 over S, like a signal in the frequency domain, looks like a constant. But here it's, now we have this 5 over S. Let's take the 5 out, since that's not going to do anything. It's just scaling. So we now have 5, 1 minus z to the minus 1, z transform of 1 over S. And if you wanted to think through what's happening, you could now say, oh, what's going to happen now? This was the handshake and a wink. What's happening with this script z? Well, first I have to inverse Laplace transform 1 over S. Then I sample, and then I z transform that sampled waveform. What happens when I inverse Laplace transform 1 over S? That's just a constant, isn't it? 1. Now I said let's sample that. So this is now going to be a sampled sample a unit step response waveform. And if you wanted to, you could say, well, that's just doing this. Right? Now, what's the Z transform of this sequence of numbers? 1, 1, 1, 1, 1, 1, every t, 2t, 3t. What you could do is you could now say, oh, let me look at, if you look at the transform table for exam number 2 in that unit, you could say, oh, if I look at row number 3, I'm going to see that in that row I have for the Laplace transform 1 over s. And now I just read across and I say, what does that look like? Well, that's now the Z transform of this sequence of numbers, 1, 1, 1, 1, 1. And what was a unit steps Z transform? Do you remember? Now you have something to do when you go to geographic location C after class on your inverted pendulum. You can go look at D2L's website. You can go, let me look in Unit 4 or under exam number 2 and look at this transform table, and you find, oh, 1 over S, and underneath that, or I'm sorry, on that same row, is the Z transform of a unit step, which was Z over Z minus 1. So now I've replaced this with a handshake and a wink, this script Z of 1 over S with Z over Z minus 1. And I can rewrite 1 minus Z to the minus 1 in terms of Z's. That's 1 minus 1 over Z. Those are unit steps. I don't know if you can tell or not, but those are 1, 1, 1, 1. For those of you playing along at home, you have no clue what I'm talking about, but just imagine somebody's beating on your wall every sample period, capital T, with a value of 1. That's what's happening in this classroom. So now we have, wow, that's going on for infinity, isn't it? So we now have 1 minus 1 over Z. If we put that over Z, we have Z minus 1. Give it a break already. But now what do we have? When we start canceling these, what was the zero order hold equivalent of a pure gain 5? We got 5 back. That seems to make sense, doesn't it? So now our discrete transfer function, when we started with an analog transfer function that was just a constant 5, our zero order hold equivalent is consistent. It's just 5. So this seems to make sense. Let's look at something a little bit more interesting than just a gain. Let's suppose now we want to find the zero order hold equivalent of a little different system, and now our system, let's pick a pure mass. That's a mechanical system. Let's find the dynamics of that mechanical system. That will be our transfer function, capital G of S, and we'll then find a capital G of Z. So suppose a zero order hold precedes a pure mass system. In block diagram form, then, we have, here is our system. Let's call that G sub 2 of S. And this is a pure mass. And we want to find G sub 2 of Z. Just for grins, let's go back and derive what the transfer function of a pure mass looks like. Because I know you want to do that when you get to destination C tonight. You're trying to make sure, or on your alphabet, maybe you're up to D. At D, you're wanting to do G of S for a pure mass system. Let's start with the free body diagram. There's our mass, and we're going to apply to that. And now don't get this too confused. I'm going to apply a force as an input, and my force inputs a lot of times in control classes are U's. So don't confuse this with a unit step, but I'm going to just say, here is my force input. I'm going to call that U of T. So U of T is overused or overloaded. But in this case, it's just a force. U of T is a force. It's not a unit step. And let's just go ahead and draw a line on in the sand. Let's say we have well, curling, you could just think this is a pure mass on a nice plane, right? And there's no resistance, there's no friction. So you have to sweep alongside that. Sorry, nobody watched the Olympics. I didn't either. But curling, I think you have a pure mass that you're trying to put somewhere down the other side of the ice. Do I have my sport correct? I don't know. I think we won gold, actually, in that sport. Didn't watch it, but I heard it. How do you hear never mind, a pure mass? Here's our line on the ice that's drawing zero, and we want to know how does that evolve? What are the dynamic behavior of that pure mass? So if we now go back to physics, and I have a mass and a force, how are those related? Yeah, go back to Newton, right? Now we know that F is equal to ma. We have Newton, so our force F was U of T, and our mass times acceleration is the second derivative of that position x. So here is what we need from physics. F is equal to ma. Written in terms of the notation that we've agreed to use, U is our force, capital M is the mass, and x double dot is the acceleration. Well, let me now solve that for the highest powered derivative, because that's kind of how we like to play with transfer functions. If I now say x double dot of t, if I divide both sides through by the mass, I have 1 over m u of t. And maybe I'm tired of writing division symbols, so I just say, you know what, forget 1 over m, let me just call it alpha. It's a gain, it's a number, so I'm just going to say alpha u of t. There's my dynamical relationship. Alpha is a constant. Equaling 1 over m. I have x double dot is equal to alpha u. U is a force, that's my input. What's the transfer function between my input and, let's say, the output, which is the position of that mass that's scooting across the frictionless surface? And if you've taken 441 or 541, this should be like falling out of your chair, that easy, right? Don't do that, please. I don't want anyone falling anywhere, not even off your inverted pendulum. If we have a transfer function, what do we have? Or what do we assume? Yes, I saw your lips wanting to say or form. What about your initial conditions? You don't have to worry about them, do you? Zero initial conditions. So now we have initial conditions are equal to 0 and finding a transfer function. We're just trying to find the dynamics. So if we Laplace transform x double dot is equal to alpha u, what do we have? What happens when we Laplace transform a derivative? We multiply by s. Now we've differentiated twice, so what are we multiplying by? S squared. So now we have s squared, capital X of s, the Laplace transform of little x of t, is equal to alpha u of s. Now we can find our transfer function. Our transfer function, capital X of s, is alpha over s squared u of s, and this in the box, not the penalty box, but in our box here, it's g sub 2 of s. Got ice on the brain, don't I? Somebody will bring a hockey stick next time, won't they? Probably, and hit me over the head with it, but we'll probably be in better shape. Wow. Spring break cannot come soon enough, can it? We have alpha over s squared. That's g sub 2 of s. We want the zero order hold equivalent of that. That's just a pure mass system. What's the formula for capital G of Z if you're searching for partial credit? You're playing along at home, right? That's now what we want, and we now need to find capital G sub 2 of s divided by s. Or this now becomes 1 minus z to the minus 1 z transform of, what was g sub 2 of s? I know it's cold in here with all this ice, but what's g sub 2 of s? Alpha over s squared. So now if we divide that by s, what happens? Now we just have alpha over s cubed. So now we put that inside this curly bracket. And we have alpha over s cubed. Does anybody ever remember inverse Laplace transforming 1 over s cubed? What happens when you inverse Laplace transform? Let's work our way up to this. What happens when we inverse Laplace transform 1 over s? Laplace transform. So now what happens when we inverse Laplace transform 1 over s? I'm giving you the answer, 1. Now I can't give you the next answer. What happens when we inverse Laplace transform 1 over s squared? Okay, so now we had 1 over s was constant. 1 over s is like what kind of operation in the time domain? Integrating 1 over s. What happens when we integrate a constant 1? We get t, do we not? So now if we inverse Laplace transform 1 over s squared, we have t. We went from 1 to t. Now what happens when we inverse Laplace transform 1 over s cubed? T squared, but we actually have a factor of 1/2 sneaking in on us. And it's actually 2 factorial, but 2 factorial is 2, so it's really just 2. But we now have t squared over 1/2 t squared is the inverse Laplace transform of 1 over s cubed. So that's now what we have to sample and then z transform. So now we have this parabolic in time that we're sampling, and we want to then z transform that sequence after sampling. What are we going to do? Well, we go into our table and we find 1 over s cubed in that table, its Laplace transform. We read across and find the z transform associated with that, and it gets a little bit interesting, but we can do that, right? When we just did that for a constant, it was z over z minus 1. So you would expect maybe to see some more z minus 1s in the denominator. Here's what happens. G sub 2 of z is now 1 minus z to the minus 1. Let me factor out the alpha and the 2 so that I now just have the inverse Laplace transform of 1 over s cubed, essentially. But this is now in that table, the sample period squared, that's just a number, z plus 1 over z minus 1 cubed. That's what happens when you look at or find row number 2 in the table of transforms for exam number 2. Again, as you're making your way through the alphabet and your way home, maybe at E, you look at row number 6 in this transform table and you find that 1 over s cubed becomes t squared over, or t squared z plus 1 over z minus 1 cubed. But we can clean that up. This 1 minus z to the minus 1 is z minus 1 over z. We have an alpha over 2, and we have here t squared z plus 1 over z minus 1 cubed. Do you see all the cleaning we can do? We can get rid of a z. We can get rid of one of these z minus 1 factors. And what are we left with? Now the zero order hold equivalent of a pure mass is alpha t squared over 2. That's just a number. Alpha was 1 over our mass. T squared is just the sample period squared divided by 2. And we're left with, in terms of polynomials in z plus 1, z minus 1 squared. Now you're probably wanting to know what is that? Well, if I said what's a pure mass in the S-plane pole zero diagram, what would you have? That looked like a 1 over S squared. What's that? In a pole zero diagram, 1 over S squared in the S-plane. How many finite zeros do you have? 1 over S squared. How many values, what finite values of S cause the numerator to vanish in 1 over S squared? None. You don't have any finite zeros. Where are your poles? At the origin. How many poles do you have? 1 over S squared. You have 2 poles at the origin because you have S squared. What do you have here? Let's just plug in some numbers. Suppose our mass was 1 kilogram. So alpha is 1 over m is 1. And let's just, for grins, pick a easy sample period, capital T, so that what's g sub 2 of z become? What's that look like in the z-plane? Pole zero diagram. Where are your poles? At 1, how many do you have? Those are on top of each other, but I'm staggering them so that you can see. Do you have any finite zeros? Any finite value of z cause that numerator to vanish? It's at -1. You have a 0 over here at -1. And we're going to learn that -1 is like infinity in the z-plane, because that's what? Halfway around the unit circle. It's on the unit circle. That's as far as we can go frequency response-wise in the unit circle. We now have 2 poles and a 0. Sort of like we had 2 poles in our analog plant. We'll pick up at that point on our next visit, somewhere in this icy lecture hall. Good luck getting home on those inverted pendulums.